I don't think that was necessary. Like, I don't think it was. That probably means that like.
Okay, let's get started. Are you ready with the camera? Yes. Okay, perfect. Great. So today we have a couple of things on our agenda. First, I want to talk a little bit about the exam, which is coming up next week. So what can you expect? Then I want to do like one big piece of the exam is going to be critiquing and redesigning a visualization. And I just want, like, we've done this in class here, but I just want to go through some of the factors, and you can kind of like use this as a template on how to really like critique a visualization across a set of dimensions. Then we'll do the exercise of like brief recap about interaction that I kind of like couldn't get through last time, and then we'll switch over to multiple coordinated views. For the exam, everything that I covered up until the end of the lecture is on the exam. Everything that's covered on Tuesday is not anymore. So that's kind of like the content that you have to study. And all the slides are already online except for today's, and I'll upload today's so that you, after the lecture, so that you have all the material you need to study. Okay, great. So the exam is going to consist of 5 different types of questions. First is going to be theory questions. Like an example would be, what is bad about the rainbow color scale? Anybody can answer that? Yes. So that's not a hard question. These are, of course, examples, right? Which channels are good for quantitative data? This kind of questions is what you can expect here. So this is fairly like straightforward. What I'm teaching here when I teach a theory lecture, you kind of need to answer these kinds of things. And then there will be like a design critique. You will be given like a visualization, and then I'll ask you to analyze what is good or bad about the design, and I'll ask you to redesign it. Maybe 1 or 2 different versions of your redesign, and then you should argue why your redesign is better. And so we'll talk like more about this in the next couple of slides. Since we also had like about 50% of our lectures were about technical things, on the first exam there will be questions about HTML, D3, JavaScript. So for example, all of those questions are going to be high level. I'm not going to ask you exactly what are the parameters of the scale function. I'm going to ask you things like, how does data binding work in D3? How do you access data in D3? Where is the data bound? Where is the bound data stored in the DOM? What is the DOM? What is the relationship of the DOM and the HTML? These kinds of higher level conceptual questions. And And there's going to be a find the bug question. So there's going to be like a code snippet, and you will need to analyze that code. It will not produce exactly what it should produce, and you will need to find what is the problem and how can you fix it. This is going to be like, again, not some subtle syntactical or like wrong signature thing, but it's going to be something about like how you really structure D3 code. And then finally, for the grad students, there will be questions about the reading. So the 2 papers that we discussed in class, like definitely take a close look at those again, about the crowdsourcing, graphical perception, and the interaction paper by Jeff Hare and Ben Schneiderman that we read for last week's class. So that's kind of the structure. Any questions about this? Yes?
Sorry, you mean just those 2 readings?
Those 2 readings, yes. Like we have a lot of other readings, right? But I'm basically anything that is on those papers, again, big picture things, not like little details, is fair game.
Are we getting different tests, undergrads and grads?
No, we will say like since there's like 90% grads in here, the undergrads will get the same test, but it will just say grads only on the question, and then if you're an undergrad, just leave it out. There's no bonus points for the undergrads if you answer the question.
Is it completely free response?
It's going to be free response mostly. There will be like the code stuff. You will highlight something. I haven't assembled the exam yet, so there might be like it's not going to be multiple choice, but there might be some structure in some questions. Yes.
Do we get to bring notes?
No, it's a closed book exam. Okay, this is not gonna. It's supposed to be super stressful. It's only 10% of your grade. It's really just so that like I give you guys an incentive to review the material. Okay, so now let's talk about critiquing visualizations. So first thing that if you want to critique a visualization is like definitely do identify the data, the tasks, and the intentions. Like it's tasks and intentions aren't always obvious, but very often just based on what the figures or the like you're gonna get figures what the visualization shows, you can kind of like infer them. So for example, if you have a quantitative time series visualization, you probably want to like the author probably wants to communicate change over time. If you have qualitative labels, that is often like a supplementary piece of information that brings in context. You also want to, like if you have quantitative in 2 conditions, like somehow separated or color highlighted, then like you probably want to compare. So like here, like when I talk about identified data, recall the lecture, we had basically like high level qualitative versus quantitative data. We distinguish between interval ratio and ordinal data in addition to that. And then you should, of course, also think about what are the labels, what are the independent variables, what are the dependent variables, and so on. So what is the data in this example here? Is it qualitative, quantitative, both? Yeah.
Qualitative data about how you feel towards science.
Qualitative, like or like these are categories. They're categories, but they're also we have numbers about the categories, right? So you have these 5 response types, which are kind of our in this case our labels. But then we have the numbers, so we have 10% are bored, for example. So this is like a quantitative piece here. And we have 2 different conditions here. So very likely, like again, like this would be like the categorical data, like before and after, and very likely the person that made this chart wants you to compare those 2. So that's kind of like how you would approach this one. After you've identified the data and kind of the intention, you should also think about marks and channels using the vocabulary we talked about. So just recall that a mark encodes the existence of an item. It can be something like a point, line, a shape, or a volume, something like that. And the channels encodes the magnitude of the dimension associated with an item, magnitude, or it could be for qualitative categorical data, it could just be the type. And here we use the channels. The common channels are position, size, saturation, color, angle, and all of these kinds of things. Just like, I'm sure you remember this from the lecture. So let's say this one here. What are the marks?
The dots.
The dots. Any other marks?
The red lines.
Yes, we have the red lines here, which show us some statistical information. Great. What is the channel?
Position.
Position. Yes. And can you be more specific? There's two types of position used here.
Vertical position.
Yes. Vertical position encodes the numerical quantities, and then horizontal position encodes the categories. Right. So we have these border shading, interval only. So this would be like an example where we like facet by a category and then plot the quantitative data with position using the dot as a mark. What about, what's the mark here? A slice, but more generic. Term would be an area or a shape, right? I would say like shape is probably the most generic response here. And what is the channel?
Color, position, and size.
We have area. So area is correct, but there's also, you could also argue that another one is correct.
Angle?
Angle, yes. So both of those are of course correlated, right? Like larger angle, larger area. And then color here is really not encoding a ton of data, right? So color here is really just to separate the segments. So there isn't, this is just like basically every item has another color or should have another color in this particular example. So remember this one. What are the marks?
Shape blocks.
The shape blocks, yes. What are the channels?
Color.
Color? Size? Anything else? Position, yeah. So they are kind of positioned and grouped together by these major categories. The third thing that you should consider is the effectiveness principle followed. So, like, remember, the effectiveness principle is really about using the best visual channel available for the most important aspect of the data. And so, like, that's the question you should ask yourself: is like what the visualization shows, is this encoded as efficiently as possible? And you should argue by using the rankings that we talked about. Like, remember, position is the most efficient encoding, and you should argue this by like Stevens' psychophysical power law, so that we have this relationship between physical intensity and perceived sensation, which has a linear relationship only for length. And then the second question you should ask: are all the visual channels appropriate? Right? It's not only a ranking, but some people like encode quantitative data with color, and then you should argue, well, it doesn't really make sense to encode quantitative data with color hue because there's no inherent ordering. Yes.
Is there any situation where electric shock is appropriate?
As I said, Stevens didn't study this just for visualization. He studied this for general human sensation, and so this is just an illustration. So do not encode data as electric shock. Your exams will not have a visualization that has electric shock. Okay.
Was it seeing electric shock or experiencing it?
It's experiencing, yes. Here, is the visual channel appropriate? Remember this example about crime in New Zealand? What did we say here?
No.
No, and why not?
Because they encoded it based on radius instead of area.
Exactly. And if you think about it a little bit more, even area wouldn't be the most appropriate one, right? So you could say, like, you could have encoded this more efficiently by using position. But you could also make an argument, and like this isn't a simple formula. You could also make an argument that, but given that this is a newspaper article and just showing a bar chart might be fairly boring, the author might have tried to achieve grab people's attention, and maybe therefore the bubble encoding is justified. So it's not like completely black and white, right? But clearly, like the way this is done here is done wrongly. And then here would be a redesign for that we looked at, just like showing it as a line chart. Here we are using position and changes over time. The fourth thing to think about when you critique a visualization is the expressiveness principle followed. And that is the visualization should show all of the data and only the data. And I would kind of like qualify this. If there are violations of the expressiveness principle, are they justified in some way? Like, is it useful chunk, charge chunk? Like we talked about when this monstrous cost and the diamonds are a girl's best friend example that kind of draw people's attention in. So like there can be good reasons to like add extraneous elements, but then we had this example where we have extraneous elements with, and it doesn't really like make it a better chart because of that. Like you should never sacrifice readability to like a large degree for just like a graphical effect. The one thing that you frequently see are scales. And this is the whole lecture we talked about when we talk about designs. Are the scales appropriate, right? Is like, it's not only do they start at 0, but are they like appropriate to show the effect that is in the data? So here in this example, clearly, if the Bush tax cuts expire, the scales are clearly not appropriate because it's overemphasizing the effect. Do you remember what this is called? If we have this this difference between the graphical effect and the effect in the data. How did Tufte call this? The lie factor, exactly. So the size of the graphical effect should be directly proportional to the effect in the data. So here is this example in a redesign chart. Also notice that there is a lot more subtlety to this chart because it's not only 2 bars, but it also gives you more historical context. And context is kind of the 6th thing to think about. Is the data shown in the appropriate context? So we had this example about climate change. When you only pick like 4 or 5 years, you can't see a trend. But if you like pick the appropriate context for the effect you want to show, then you can actually see something in the data, like this one here. So here clearly this doesn't show like a strong effect, but if you like choose the appropriate context for the data, then the trends become readily apparent. A little bit more subtle is the question, would some kind of data transformation or derivation be better? So for example, show the change of the data instead of absolute values, or show a distribution instead of data points. So we had a couple of examples like this. I don't have any here. But remember that we had this fertility distribution over time with the animation, and that you could actually just like create a completely different chart with a little bit derived data to show like what is actually going on in a much more succinct way. Or, for example, if you had a chart that shows, let's say, income versus cost, and what you really want to show is profit, you could do like a data derivation. So think about whether given the data that you have in a chart, you could, and the message that like the author of the visualization wanted to communicate, could you do some transformation to make the data more accessible? And then here's a list of other guidelines that are a little bit more specific. So like we talked about no unjustified 3D. Why shouldn't you use 3D if you don't have a reason for it? It's hard to interpret, like specifically. It's kind of like hard, even if you have a scatter plot, you can't really say where a point in a 3D scatter plot is on certain scales. Other problems with 3D?
Occlusion.
Occlusion, yes. What about color use?
Shadows and things like that.
Exactly, we have shadows to really make 3D appealing and have a good 3D effect, we need to introduce lighting. And lighting can influence color. We talked about this in perception, right? Like how we perceive objects that are at the top as lighter because we assume that the light source comes from the top, and so on. Then another thing that is like fairly obvious: time progresses linearly. If you have a temporal chart, clearly it should show time linearly. You should always think about all of the perception principle. So, for example, if you have a red-green encoding, clearly, like you should say in your critique that this isn't really accessible to a lot of people because of red-green color blindness. Think of the Gestalt principles. Think of figure and ground. Does it make proper use of grouping features and so on? Does it make use of pop-out for some highlights, or does it not? You're not going to see a lot of interaction animations on a paper-based test, but this is something that you should, of course, consider in a real-life example. Are the interactions and animations well designed? And then this is important here. Do you have appropriate legends and labels? Is the visualization kind of self-explanatory? So yeah, this is it about critiquing a visualization. I'll put those slides online too. But this is essentially also what we've used so far. Any questions about this? Cool. So then let's move on to like a quick recap.
Sorry, I have a quick question.
Sure.
For a test, obviously you can go on and on with like paragraphs about what's wrong and how to fix it. What are we expected to write?
Be succinct because we need to read it and you need to write it. But just like hone in on the main points. Right? Usually people tend to write too much, and the correct answer is often like 4 bullet points. So like our sample are like, as I said, I haven't compiled the test yet, but from previous years, the correct answers, the answer key is usually very short. You can write like a lot of text about it, and sometimes it's correct, but text length doesn't seem to correspond to the points that people get on the answers. So don't overly, like if you don't know the answer, like don't try to just put a wall of text up there and hope to hit it. Okay. But yeah, I do expect that on the critique piece, you will probably write a little bit more than on some of the other points. But kind of like, you don't have to write prose, right? You can do bullet points and like short, structured text. Great. So, quick recap on interaction, unless there's anybody else with a question. Good. So when we talked about interaction, we had the spectrum from static content to dynamic content. Static content would be infographics or books or paper, or what you have in like also like on infographics. And dynamic content could either be animated, which is kind of an autoplay like videos, or you have interactive content where changes are the result of a user interaction. And so, like, I asked the question, why do we actually interact with visualization? I think there's like 2 main reasons for it. We kind of like want to use interaction when we need to explore data that is either big or complex. So there's too much data, or there are too many ways to show it. And we can also use interaction to kind of like change our visual encoding to tell a couple of different stories. And so we talked about this example here, how interaction allows us to like first get an overview and then drill down into the details about these tax rates for companies. We also said that interaction amplifies cognition, because if we manipulate something, we can really understand cause and effect much better. Like the example we used here is this plot of the principal components of the input data set and the output principal component analysis. Then we talked about direct manipulation. Like direct manipulation is when you interact directly with an object and you get continuous feedback and updates. So, for example, did you select the points here directly in the scatter plot versus if you had a slider on the side or 2 sliders on the side for the x and the y dimension, that would be indirect manipulation. And so, like, the alternative would be using a query or a slider, like a textual query or a slider. And then we talked about a couple of different types of interactions, single and multiple view. And we mostly focused on single view because we have multiple views today. changeable time, navigation, semantic zooming, filtering, querying, and focusing context. And so this is going to be covered in today's lecture. For navigation, we have these operations like pan, zoom, and rotate. Rotate is especially important, of course, in 3D structures, like if we had an MRI scan, like here at the bottom, or want to navigate on a globe, we use these kinds of interaction modalities. Then we talked about semantic zooming. Semantic zooming is kind of a fancy version of zooming, where you interactively adapt the detail as you zoom in, so you reveal more about something that is abstracted in the zoomed out version, in the zoomed in version. The example we had here is that in this data center performance monitor, as you zoom into like a particular instance of interest, you suddenly get like little spark lines for like at this scale, but if you even make it bigger, you get like full-on line charts with labels that are interactive. And for semantic zooming, you usually use visual encodings that are readable at multiple resolutions. When we talk about focus and context, this was really all about carefully pick what to show as like your focus piece, and then hint at what you're not showing, so that people like are situated in the larger data set. And so this is kind of like a synthesis of visual encoding and interaction. For example, use a selective region of interest, the focus, through navigation or selection, and then you as a visualization designer provide context through aggregation, reduction, or layering. So here was one example. This is kind of like a timeline visualization, a theme river, and you have like a long time period, and then you want to kind of like zoom into one particular time period that you're mostly interested in. Here, this is from like, this is like time of day. So here we're looking at the like late evening in detail, and we have the rest of the day here as context. And we have two different zoom levels for the details. So here, very zoomed in the middle, and then continuously less zoomed in. And so here you also get all of the labels, whereas in this context region, you do not get any of the labels. We mentioned this idea of degree of interest functions. Degree of interest functions are super useful for like where you kind of like specify two terms: the a priori interest, like how important is a specific item in the data set in the first place, and the distance to a current selection. So given I have selected y, how far is x, and how far is x from y? That is kind of the term in this degree of interest function. And so that kind of like, for every item I have in my data set, that gives me an importance term, and I can use that to render it. And this like sounds abstract, but this is actually very useful in many contexts. We talked about distortion when like that it was a big thing a while ago, that geometric distortion, for example, on the map was kind of thought to enhance like what we can see in a focus region while still making the context accessible. So we had things like the perspective wall or hyperbolic geometry or these kind of linear charts, but then we also talked about that this is not necessarily always easy, because especially if you have like this in 2D, like here, it kind of can be tricky to navigate. It can be tricky to do spatial judgment. We have this whole tracking distortion that makes it more complicated. You have to communicate the tracking distortion. It's really like it gets more difficult to click on a specific item because you're moving a lens instead of just a mouse pointer. And so like recent research shows that this is not always particularly effective. And then in contrast to that, like what is super effective and is like one of the staples of interactive visualization is filtering and dynamic querying. Filtering is also called brushing or selecting, and these are kind of like very related. And so we talked about Schneiderman's mantra, the visual information seeking mantra, over, reverse, zoom and filter, then details on demand. We like he illustrated this on this example with the dynamic queries here, where you kind of like zoom and filter, like where you have overview first, so you see the whole map, all of the homes. You zoom and filter on the homes that you're interested in by expressing a query, and details on demand would be if I hover over one of the nodes and then get a tooltip with all of the context about the house listing here. And these dynamic queries are also what we now see in non-visualization applications. For example, when we do faceted search, here we look for a television that has a certain price range, is at least this big, and maybe is from one of those two companies that I trust. Okay, so now I want to do this redesign exercise here. And so what I would like you to do is to take this idea of the home finder, and remember, you can specify here two different points or multiple points on the map, and you want to specify a distance to those points, and then you want to say, I want to have so and so many houses and so on. And I would like you to create an alternative design that shows that includes direct manipulation. So remember, here we use sliders, and I would like you to use direct manipulation instead. It also shows the distribution of homes across the variables. So for example, how many homes have 3 bedrooms, how many homes have 2 bedrooms, and what is the price distribution and so on. And then also think about sketch an alternative interface that uses 2 different criteria. For example, I might be willing to drive 10 minutes more if I was to save $100,000. Something like that should also be possible with your interface. And we'll do this in teams of 2 to 3, and I will give you guys 15 minutes to go over this. So here are the handouts. Okay, so let's talk a little bit about this. So we have three different criteria: direct manipulation, show distribution of homes across variables, and then sketching an alternative interface to use different criteria in different areas. Which of those three was the hardest?
The direct manipulation was hard to think about for me.
Yeah, so what did you try here?
So mostly, I mean, it's hard to do direct manipulation to like put the number of bedrooms that you want on a map, but mostly you're going to be manipulating the area,
Yes.
which would be a lot easier if you had an actual like roadmap underneath it, so that you guys in context for what it is you were drawing over.
Yeah, exactly. So like having a little more context, and you correctly identified that area that you want to live in is probably the best thing for direct manipulation. Did anybody come up with a design for direct manipulation? Yeah.
So keeping this like circle idea, basically you create a circle for where like I want to live within this area, and then you can click on the edge of the circle and drag it closer and farther from the radius.
Exactly. So you kind of like, and the original thing, the original tool here, that didn't actually show that like a circle here, right? They only like hid the dots or the houses that were not within that criteria. But instead of like having manually like drag on the sliders here, you could just like render two circles for like your two center points where your workplaces are, and then like drag those circles around. You probably also want to show like the numbers here, like the distance, and maybe even like the time it would take you to drive between those. But that would be a good idea, yes. Anybody did an alternative or an idea, has an idea for how I would show the distribution of the homes across the variables? Yeah.
For something like price, you could have a color map, so like sort of chunk it into a lighter color and a darker color, and on the map you could see where the expensive areas are and where the less expensive.
Yeah, so you could either do like some background information for neighborhoods. You could potentially also show each of those dots could be a colored dot that encodes some attribute, for example, price, but it could also be the type. Is it an apartment or is it like a single family home? Any other ideas? Yeah.
We had a similar idea where we were using a color scale to show the price, but the user would set the median of the color scale based on their like median price, and then you would have the edges kind of.
Okay, so you would have kind of like the Virgin color scale with your like ideal price at the top, and then red above and blue below, for example. That's a cool idea. I like that. Anybody have other designs?
Something for the number of bedrooms that could just be the size or area of the circle.
Yes. So we could encode like a quantitative or qualitative variable by size, like number of bedrooms, potentially also price, right? Yeah.
So we actually pulled it out of the map and made a histogram that you would, manipulate according to the price you wanted.
Yeah. So and how, like, where did you put this?
Well, we would have like a little search filter thingy on the side.
So it's where the slider is.
Well, like
Yeah.
in this area here. Like here, you would have a histogram on top of that here, so that you kind of have a good idea of like when you manipulate one of those sliders, how many houses are you going to likely still have, right? So that's a cool idea. Anybody else did something here with distribution of home across variables? Yeah, I think this was, yeah.
This is more advanced, but you could also you could pick which variables you want to do a ratio of. So you could see like number of bedrooms per price.
Yeah. Yeah, that's a good idea. That kind of gets a little bit at the second question, right? Like if I want to have like alternative to use different criteria in different areas, I could also extend that to I have different criteria for different sizes of houses, right? Like if my dream house that has everything that I want can be more expensive than like some more pragmatic version. So that's a good idea. So I also did a redesign, and I had like some of the things, or well, maybe let's talk about the alternative interfaces first. Anybody come up with an alternative interface?
So kind of going along with the direct manipulation, like if you could draw different boundaries, you could say like this boundary over here have this criteria and this one over here. So it'd basically be like extra columns of the sliders.
Yes.
Specific parameters.
Yeah, so that's a good idea. So you will basically allow people to say, hey, I want to set up this first, like this. Like first one condition, I would have all this set of sliders, and then I would have an alternative here that would again have the same set of sliders that I can manipulate. Am I paraphrasing your idea correctly? Okay. Yeah.
Is there research done on like the effectiveness of direct manipulation? Because I think while it's very handy, specifically like drawing your own boundaries, things that are hard to put into a slider or drop down, it also requires that the user like knows that they can do direct manipulation.
Yeah, so there is a lot of research in that space. Like what you're specifically hinting at is like showing whether you can actually interact with something. So that's like a big benefit of familiar widgets like sliders and so on. Everybody knows that you can interact with. There is a nice paper by Jeremy Boy, for example, that tested out different things. So for example, if you go to a website, it would like wiggle and an element that you could interact with. And they tested out a couple of different things to kind of like show the affordances of these tools. And yes, for like generally direct manipulation versus indirect manipulation, there's also research. Not a specific paper comes to mind right now, but I definitely can look that up. So here's like my redesign. It has many of the ideas that you guys already brought up. This is like, so first I also had direct manipulation here by simply like manipulating those circles, right? So like dragging those around is like a simple way to do this. I had the same idea with showing the histogram of the distribution of those values directly on the sliders. So I didn't use any color here or any like better symbols on the map because I was using a black pen. And I think the most complicated one here is this additional, like this splitting up the two different conditions. And so here was my idea was to have like two different conditions. So here I have a distance to A, and then I have a distance to B, and I have B1 and B2, and then I split up any like price selector here on A plus B1 and just B2. So I'm not sure whether this would be an interface that like people would really get. I think this is kind of the hardest part about it, right? But I think the other two things are like obvious improvements. Any comments about this before we move on? Okay, good. So to kind of like conclude the piece about interaction, it's also super important to talk about multiple views. Like multiple views are just like how do I show things across different views, and also how do I manipulate the data in those views. And so like multiple views is again following this eyes over memory idea. We kind of like trade off display space and working memory. And so here on the right is this classification in Tamara Manson's book. We have multiple views can have either shared encoding, shared data, shared navigation, and there can be different combinations about it. And then I can either partition into side-by-side views, or I can superimpose. And this is kind of roughly the structure that we'll be talking about today. But more generally, like what are linked views? Like multiple views is just like two views. But linked views are multiple views that are simultaneously visible and linked together such that actions in one view affect the other one. And the obvious one is, of course, highlighting, right? If I select an item in one view, the same item is selected in the other view. Another option for linking them would be navigation. So do I share like navigation? For example, I have a map. One of them shows me like humidity, and the other one shows me temperature. And then I navigate, and they both zoom and pan and synchronize. So this would be another way to link. For encoding, we have kind of like the choices of same or multiform encoding, and for the data set, Do they share all of it? Do they share a subset, or do they share none of the data? And so we'll go through this now in a little bit more detail. So this is the simplest example here, linked highlighting. This is a MATLAB figure where you simply like have a geospatial plot and 2 scatter plots. When you brush in one region, all of the other elements that are the same item are highlighted in the other plots. But this is kind of like a very powerful like interaction paradigm, because we can simply like use an optimal encoding like scatter plots here and still understand relationships. Here's a little bit more complicated example. This is a tool it's called Keshiv. And Keshiv is actually was published at Viz and is now the student graduated with a PhD and then started his own company and now sells this tool to various companies. I hope it will load. Tried it earlier, it did work, so if it doesn't work, it's my internet here. Okay. That's a little disappointing. I suspect it will just take a while. There we go. So here we have like a lot of different views. This is 8 worker security. So we have a geospatial view. We have like, and these are about like attacks on 8 workers in like various countries. So we have a geospatial view in the middle. Where did these attacks appear? And then we have means of attack, attack context, the location, and then here on the right we have the country, the global region. And then a timeline at the bottom. And so all of these are different facets. Like we have all of this information for each of these attacks, but it's really hard to show them all at the same time. And so what this tool does is it simply like facets it into these kind of like bar charts or histograms, and I can like hover over kidnapping, and I see immediately what is the proportion of kidnappings across this attack context variable, the location variable, on the time variable, and then with little pie charts directly on the map. If I hover over an item in the map, it will kind of like I can zoom in and I can reveal the individual items if I want zoomed in further. I can select the country and then see all of those specific items. And I can also like filter here. Like this is not just highlighting. Now I've actually selected just the Middle East. Or some global region, Middle East. This doesn't seem to be perfectly, well, I guess, yeah, you can count this as the Middle East. So like this allows us to do like interactive highlighting, but also faceting and filtering of the data set. And so like this uses super simple visualizations to show like a fairly complicated tabular data set. And basically it relies a lot on interaction. So what we just saw here is also called multiform visualization. So we have different visual encodings that are used between views. So we have a map and bar charts, for example, and a line chart for temporal data. And multiform does imply there's some shared data, and the data is either all of the data is shared or a subset of the data is shared, and we have an overview plus detail. And the rationale here is that like a single monolithic view has strong limits on the number of attributes that can be shown simultaneously. So what I mean by that is, like, think about if I just had the map, I wouldn't be able to encode these 6 different attributes that are shown in extra views directly on the map. But by using these multiple views and different types of visualizations, I can actually show like all of the different attributes at the same time. So the different views support different tasks. The one view allows me to look at like the time. The other view allows me to look at the type. The third view allows me to look at the geographic region. for all of the same data. Here's another example. Like I have an electoral map. This was a homework a while ago. Like we're not going to do this one, but this was a homework a while ago. And so we have a cartogram here where like the Democratic versus Republican voter share is visualized in with color. And then here on top we have like the same data in a multiple view again, but in this case here showing like this in a different way. Here we also show the size of the electoral votes for each of the states. So those two views show actually exactly the same data, except for that this one here shows also geolocation, but encodes the electoral votes as numbers. The one on top doesn't show geolocation, but shows the number of electoral votes in a site. So they're complementary to show us different things, but both are useful together. So even though they show exactly the same data, with the exception of rough geographic location, they are both very useful. You can also just use exactly the same data and different idioms or visualization techniques. Like here is an example that uses an adjacency matrix for a network and a node link diagram and puts it side by side. In this paper, they actually studied whether it's beneficial to have those two simultaneously visible and whether people could do better than with one or the other. Here's another example from my own work. This is a piece that was about finding paths in networks, so that you would put in a query, like how is node A connected to node B, and then you would get a list of paths as a result. And you would get either this list of the path, or not either, but you would get both this list of the path and like this overview of like how are these all different paths connected. And they have both like pros and cons. Like here we are showing, in this case, this gives you a sense of like, this node here is really important in this in all of the connections because there's a lot of paths branching from it. Here we can show attributes about those people, and so they have complementary strengths, and therefore like, you show both of them simultaneously. Overview and detail is when one view shows like an often summarized collection of information about the entire data set, while additional views show more detailed information about a subset of a data. So the rationale here is that for large and complex data, like a single view of the entire data set cannot often capture fine details, but you want to see those fine details as well as the overview. This follows kind of like overview first mantra. So here's a simple example of that idea. You have a stacked zooming approach. So this is a little bit hard to read, but here at the top, you have a timeline that spans like a long stretch of time. And then there's two regions selected here. There's the blue region and the yellow region. And then this block here, from here to here, corresponds to the blue region. And this block here, from here to here, probably corresponds to the yellow region. And then somebody made more selections, a red and a green, and then this gray region. And those are zoomed out down here. So you kind of like have the same visual encoding, the same data, but three different zoom levels, and you just show like where they are and where they are located in the respective higher level charts. So different resolution, same data, same encoding. Here's an example of multiform overview in detail. So this is from Mariah Meyer's work. So this is like the context here is comparing two different species from a genetic point of view. So you have like the overview of a whole species, and then you can select one particular chromosome and how it relates to other species. And so this is what's shown here. And then a detailed view is shown on the right. So this chromosome 4 is also replicated here, chromosome 4, and we show this in more detail. So same data, but a different visual encoding. In this case, like a linear versus a circular. And then on the far right, I have another level of detail where I compare like one particular chromosome from one species to a chromosome from the other species. So this kind of like layers multiple levels of overview and detail here. This is another example from my own work. You have an overview. Like this is a clustering of like gene expression data. And these like little blocks here give you a kind of good sense of what is the main gist about it. But if you want to see more, you can just like pop this out and see the same data encoded again. Or here on the right, these are like little networks that are overlaid with this gene expression data. You have like 4 different versions of this. And then if you want to look at one in detail, you pop it out and show it. And in this case, all of the labels are now readable and visible. So, like in contrast to overview in detail, small multiples, here each view uses the same visual encoding, but shows different subsets of the data. So here, like earlier, we had the same data in the overview in detail, or at least a subset of the data. Small multiples use different parts of the data. And the rationale here is to be able to quickly compare different parts of the data set, again, following this eyes over memory approach. So what do I mean by that? So here's an example, again, from biology. This is from one of Tamara Manson's papers. We have, like, this is one network. Like, you can see it in big here. There's one network. This is, like, again, a biological network. And then the nodes here show attributes that were collected about them. So, for example, think of these, like, activity levels of genes. And they had 8 different experiments, say. And they could now try to show those 8 experiments directly on the node. But what they did instead is they created these multiples here. Like, this is always the same network. But it's encoded with small multiples using a different subset of the attribute data set. So this is like same underlying networks, the same layout, but different data sets for each of those conditions. And now you can compare between them and see them simultaneously. And then here again is like we also use the same approach in this example here on the right, where you see the green highlight. This is the same network, just overlaid with different subsets of the data set. Very related to these small multiples is partitioning. Partitioning is like an action on a data set that separates the data into groups. But it's a little bit more generic in some sense, because you kind of like have a couple of design choices. So how do you divide data up between views, given, for example, a hierarchy of attributes? How often do you want to split? What is the order of splits? And how many views do you want to create? And like partitioning is usually something that you do based on a categorical variable. But if you have a numerical variable, you can also create bins, for example, to create partitions. So here's an example. This is a data set, like a simple data set of age distributions in different states. In the left plot here, this is partitioned by state. So we see we have the distribution. We see that like the most common age is 25 to 44 years like across, like not across all states actually, but it's like pretty high at all states. But it's partitioned by state. So we have California, New York, Florida. What is TK? Wow. Maybe it's supposed to be Texas. Anyways, Illinois, Pennsylvania, here. So here, partitioned by state. On the right, it's partitioned by age group and state. So here, like the instead of just using the color encoding for the age group, we have like the under 5 years down here, and the Californians up here. And then the 5 to 13 here, and then the Californians here, and so on. Which of those two visualizations is better? So which one?
That one, the left.
Why?
It's easier to, it does the grouping that makes it easier to compare within a state.
It makes it easier to compare within a state. It also isn't particularly tricky to compare between states, right? Because we have the same order. So we have all the young people on the left, and I can fairly quickly scan across all of them for the first bar. And we have a lot more space to see like more variation here. So like I find this fairly like not expressive versus this is pretty expressive, in my personal opinion. One other thing that's weird about this chart here, which is also fairly common in if you talk about populations, is how to split age groups. like it's under 5, 5 to 13, 14 to 17, that's 3 years, and then 25 to 44. Not particularly surprising. Like these are meaningful categories, right? These are kind of like phases of life, but it's also like these trends are a little bit hard to like make sense of because of these like arbitrary splits. Who's seen the like iris data set in machine learning? So this is like a common data set that you use to like explain classification problems. You have 3 different species of iris, and you usually color code them in the same plot, but you could also facet them. You could say, I'm kind of like separating all of these 3 different species out and show them in their separate plots. And that, of course, is the advantage that I don't have any like overplotting and I can see them completely separated in each of these dimensions. So like an example that takes this principle to kind of the extreme are trellis plots. And trellis plots, and I'll show this in more detail if you can't read it right now, but trellis plots essentially has like panel variables. These are quantitative attributes that are encoded in individual views, and then partitioning variables that partition the attributes and either assign them to columns or to like subsets of the rows. And trellis plots also do an ordering. I'm going to skip over the ordering for now. And so let's look at this particular trellis plot here. The data here is barley yields in 2 years across multiple farms for multiple barley strains. And so the year was used to partition it in like horizontally. So you have 1931 on the left and 1932 on the right. Then the farm was partitioned vertically into, like here you have the Waseca and then the University Farm, and then Morris and Grand Rapids and Duluth and Crookston. And then the individual barley strains are shown as rows, and then you have the numerical values for the yield for each of those barley strains. And so you can now compare between 2 years and between multiple farms at the same time by just like moving your eyes around here. What do you think about this visualization? Yeah.
Feels cluttered. Like you have to be trained, I feel like, to be able to utilize it well.
Yeah.
Also, the scale, they're replicating the scale on each side, and because of human physiology, it probably makes more sense to mirror it.
That's a good point. Yeah. So you could mirror it. You could replicate it. There's like I think it's only like there's a couple of some minor design things that aren't quite as great. So for example, why don't you show the labels up here, but only on the right? So that doesn't make a ton of sense, right? And anybody have another opinion?
I think the 2 columns are redundant. You could color code the years within 1 column instead. So
Yeah.
you could actually compare.
Exactly. So that's a good point. Sometimes it's useful to layer instead of partition. So here, this is color coded now by year, and now we can do like a better comparison of years before and after. Yeah.
What does the orange on the right represent? It seems to just be halfway through.
Orange on the right. So this is, you mean this in the headers here?
On the right graph, there's the green bars and there's orange.
Yeah, so those are just the facets. So you see that the left one here is, the left column here has the orange on the left, the right column here is the column on the right. So that just like shows where it is. Like it's better explained actually here. So you see, like this is one facet, this is the second facet, the third facet, the fourth facet, and so these kind of like just indicate how this was split. That's what's in the header of these bars. I agree this isn't a particularly useful encoding, especially if you just have 2 of them, right? But like the main point here being actually that we split it out or layer it in different ways. Any other comments? Yeah.
It's still fairly difficult to like compare the 5th axis of Waseca versus the 5th of like Morris or something like that, right? I think if you could add some form of interaction, then you'd be able to like pull those out and be able to directly compare.
Exactly. And so what you're bringing up here is like, if your task is to compare like the strains, you might have split it differently, right? You might have, instead of splitting it by farm, you might have split it by strains. So like that's basically a choice that you have to make. What do you split on? And like it's quite common to actually have data where you have these multiple categorical attributes that you can choose to split. And if you give people the power to like do this splits interactively, you create like a fairly powerful analysis system, but it's also not completely easy to use. And I'm actually going to show you a tool now that gives this power to do these splits interactively to people. And so like we talked a little bit about tree map in Tuesday's lectures, and we'll talk more formally about tree maps when we talk about tree visualization. But here, like this is a map of the market. So like the stock markets, you have like sectors like healthcare, financials, oil and gas, consumer goods, and so on. So this is like your top level split. Here, like you could think of these tree maps as partitioning, like allowing you to flexibly transform data attributes into a hierarchy. So I could, for example, split by sector, and then I could split by profitable versus not profitable. Then I could split by non-profit versus for-profit, or any kind of attribute that I wanted to do. And tree maps basically are just one example of doing this. And these guys, this is like Alan Slingsby from London. Yeah, they have kind of like took this idea of partitioning with tree maps like to the max. So here, like I'm showing you housing data in London property market. And as you can imagine, you have like for houses in London, you have like attributes such as what neighborhood are they in, what's the house type, when were they sold, and so on. And then you have like numerical attribute like the price, the number of sales. And so what they're doing here is they're partitioning first by the house type. So you have the flats on the left, the semi-detached houses on the right, and the terraced houses on the bottom right. And then they again partition it by neighborhood. So for example, within flats, you have rent here. And then you will have rent somewhere in each of those, but you would have to find it. So that's a little bit trickier, but it's definitely there. And then it's again partitioned by sale time on this smaller scale that's barely visible now. And then to encode attributes, they encode average price as color and the number of sales as size. And so as the result is like you can compare between neighborhoods different housing distributions. So you can kind of see that we have certain, like if you have rent, I finally found it. Here is Brent and flats, and then here is Brent in semi-detached houses. And you can see there's way less sales of semi-detached houses in Brent. What you also see is that for a certain house type within the neighborhood, we have pretty similar prices. So there's some outliers, of course, but generally, like Brent, for example, here is fairly consistent. Like up here, this is like we have some outliers. But I could take the same data set and kind of slice it completely differently. So I could slice it first by neighborhood, then by house type, then by sale time in year, then by sale time in month. And then I could encode neighborhood location approximately so that I have like the neighborhoods that are in the center of London, somewhere in the center. And then I could use average price as color. And then I couldn't actually, like I could chose not to use size and just have a uniform size. And so what I can see here is that the price depends a little bit on the distance to the city center. So here's a video that kind of demonstrates this tool. And I also wanted to say that this is a pretty nice, a pretty cool grammar that they developed for this.
This video accompanies the 2009 paper of the same name. It demonstrates how hierarchical layouts can be used to explore multivariate data through the reconfiguration using London property transactions as an example. We run through all the figures in the paper using the notation we developed to describe their states, the operators we use to reconfigure their states, and showing how this can help us address research questions. Property transactions in this view are conditioned using property type and the year of sale. Rectangles are sized by the number of sales and coloured by the average price. Almost half of all sales are flats. Since rectangles are ordered by size, temporal trends are difficult to detect. We will now reconfigure the layouts to arrange the years chronologically. This view more clearly shows the upward trend in average price. To increase the temporal granularity, we will add none to the hierarchy. We also recolor to reflect the number of sales. We call these calendar views. Years are arranged from left to right and months from top to bottom for each year. Purple is used to show the number of sales, which appear to vary seasonally. We expect there to be spatial variation in these data, so we will now insert London Borough into the base of the hierarchy and use orange to show average price again. There are marked differences in sales, shown through size, and price, shown through colour, between boroughs, but it is difficult to see how this varies spatially, as all the rectangles are ordered by size in the top left. We can see, however, that Wandsworth in the top left has the most sales, and the City of London has the least. The size order doesn't let us identify spatial patterns very easily, so we now rearrange the rectangles spatially and separately. We can now detect some spatial patterns. For example, we can see that the highest average prices tend to be central and west of the centre, and sales of flats dominate centrally, but less so peripherally. Rectangles are small where there are low sales, making it difficult to see the detail. In the next view, we fix the size of rectangles to show each with equal prominence. The detail of property types can now be resolved more easily, even where sales are low. To study how much each borough differs on the average ratio.
Okay, so you get the idea. So this is really a cool way of slicing and dicing a data set interactively. What was also very impressive about this particular presentation when they gave it at this conference is that they hacked all of the commands that you saw there live. So they really did a full live demo for 15 minutes, coding and dynamically adjusting the visualization. So that's pretty cool. Okay, so we talked a little bit about layering already because we brought up this comment earlier, but layering really is combining multiple views on top of one another to form one composite view. And so that is of course great if you have a large, more detailed view that you can explore. You kind of but have to be wary that you can only layer certain things, so it imposes constraints on your visual encoding choice as well, on the number of layers that can be shown, and on what kinds of data make sense to be layered. So here, let me give you a very traditional example. Line charts are great for layering, right? I can easily layer the exports of multiple countries on top of each other, or exports and imports, because they use the same scale, they have semantically similar things, so I can actually layer on a line chart, I can layer many lines. Of course, there's a limit, right? At some point, it just gets way too cluttered, but generally, line charts are very amenable to layering. Using different charts is also possible, so this isn't necessarily a terrible visualization here, because we have bar charts and line charts. We have the same scale shipping, same scale shipping cost and profit. So this is okay. You can layer these kinds of different charts, but you shouldn't layer stuff on each other that doesn't really belong together. So here, don't do dual axis. Here we have a chart of number of people who drowned by falling into a whirlpool, and number of films Nicolas Cage appeared in. This is kind of these spurious correlations, right? But essentially, you can fiddle with scales and so on to kind of make this appear easily. So usually you shouldn't use multiple scales on a single chart. So you shouldn't ever use one line chart, one type of lines, one scale, and then overlay it with the other one, because that gets really, you really have a lot of choices to make, and that gets really tricky. You can also combine partitioning and layering. So here, this is again from one of Mariah Meyer's papers. This is a time series experiment for different species in a phylogenetic tree. That's what you see on the left. And you see all of these time curves here in the middle, and they're kind of split up across another dimension, and I don't want to go into details here. So you see every detail here, but then at the bottom, they are also layered by these groups, and then here they're layered by species. So you have a combination of layering and partitioning here to kind of see details about each of them, but also see the overall trends. And then you can take this multiple coordinate view idea to the max, and I'm just going to show this very briefly. This is one of our papers where we played
for extracting, comparing, and manipulating.
So we played with how can we combine multiple views together so that you can see a fairly that you can create pretty complicated data sets using multiple views and their relationships. So let's skip to some interesting piece here. So here you can kind of like keep building a visualization. So you have a heat map, and you have some axis-based visualizations.
Blocks can be transposed.
Then you can add scatter plots and see the relationships between all of them, and you can track new data into the canvas. And all of them are linked, like really with explicit links, but also, of course, through highlighting.
Sorted. And enhanced with weights.
Okay, so this concludes it for today. And we'll see you guys on Tuesday.